Okay, we will be doing transmission lines top chapter today. Transmission line is a medium of transmitting power or signal from one place to another. These are the objectives and the outcomes. And first in that we will start waveguides and cavity resonators. Now in waveguide and cavity resonators we have, you can see this is the propagation characteristics of uniform plane waves in free space. So here you can see E and H, they are orthogonal to each other and they are traveling. This is the direction of propagation of a wave. So this uniform plane wave is TEM wave because E and H, they are perpendicular to the direction of propagation. And as the waves propagate, we can demarcate these different regions around the source of propagation, source of radiation. Suppose this point is radiating electromagnetic wave, so the region around it can be divided into different regions. First is your reactive near field region, then we have a Fresnel zone region. These are the boundaries specified. And then we have a Fraunhofer zone, and then we have ideal plane wave. So like d square by 4 lambda reactive near field region. In this region, in this you need 2d square by lambda. So this is in this region below this, here the energy is stored, not radiated. It is stored in EM waves. So that is why it is the region where energy is stored, where region after this is the radiative region. That means region where the energy is propagated or moving away from the source. So this 2d square by lambda is the main demarcation between near field region and the far field region. For transmission between power amplifier to antenna, it is necessary to confine and guide the wave energy from point to point as desired, so that there is no leakage of energy. So guiding structure is very important between the amplifier and a radiating structure. In such the fields are confined or restricted by boundaries of materials differ from those transmission path, and the waves are said to be guided by these materials. And again how to find out E and H field at every point within the guided medium. So for that you have to apply Maxwell's equation, and you have to solve it using boundary conditions to get the E and H solution at every point within the guiding structure. The study of guide wave is most easily approached by first merely confining the field between two parallel plates of perfectly conducting material. So first we consider two parallel plate which are the guiding structure, and these two it is open from all sides, only guided from top and bottom. So if you see this diagram, it is bounded by your ZY plane only. That means two plates in the ZY plane, the wave is guided. So and then the study of this can be extended to a wave which is guided on all four sides, which is bounded by all four sides. So here you can see okay. Now field equations between parallel plates and propagation parameters, we can see that the structure condition is plates are extended to infinity in YZ direction and the plates are perfectly conducting. The plates are separated by distance of A, as can be seen from the diagram. Let me enlarge it. You can see from the diagram plates are separated by distance A, and the space between plates is air or free space. Here we consider dielectric is air, and the direction of power flow is along z direction, and all field components in z direction vary as per this. In the z direction it varies as e to the minus gamma p. Gamma p is the propagation constant, which consists of attenuation constant and the phase constant. This way it varies along z. As if the wave propagates plus z direction, so here minus is written, minus gamma z. So propagation constant is complex. The real part defines attenuation, imaginary part defines propagation or the phase shift, phase constant. And in time varying form, what we do, we multiply by, if the wave is if a wave is varying but it's a harmonic field, then e to the power j omega t is multiplied along with this. So this is the most popular way of writing e to the power j omega t minus beta p z. Beta is the phase constant along z, but actually it should be gamma. But if we take attenuation 0 in the sense the dielectric is lossless, but if it is not lossy, then attenuation 0, then we can just put the phase constant here. And then to solve the equations, you can see these are the Maxwell's equations that we know very well. Curl of H is j omega epsilon 0 E, curl of E is minus j omega mu 0 H, and the wave equations, by traditional way, if we solve these Maxwell's equation, we get these differential equations in this way, which we call Helmholtz equation. And then by going by the traditional calculation, taking the curl, equating left and right side, we can easily form these equations. So they are very easy, they can be easily formed. Just you have to solve, take the cross product, equate real and imaginary on left and right side, then we can get these equations. And then they can be solved simply differential equations. The way we solve, we get these equations in this way. So this is pure mathematics, just solving differential equations. E can be written as, here you can see e to the power 0, that's the magnitude, e to the minus gamma p z. This, in this form we can write any wave, any field vector. Any vector can be expressed in this form. So this, if we substitute in these above equations, then we get this. That means these mathematics are easy. The wave equations, we obtain this in this form. So these are the final form. You can see second order differential equation is there, where this is phase constant and other. Actually here points to be noted, in these two equations E and H are decoupled. That means this full equation is in E, this in H, which can be solved. So here, and once we solve this, we get hp square gamma p square omega square mu 0 epsilon 0. Now from these equations we see that if Ez is 0, z component is 0, Hz is 0. As in the case of uniform plane wave, all components will vanish. If you make Ez 0, Hz will be 0, and from these equations you can see other field components will go 0. Therefore there should be either E or H longitudinal component, that means in the direction of propagation. So that is why we cannot have TEM wave in waveguide. So transverse electric waves we can have, or transverse magnetic waves we can have. At least one longitudinal component should be there. Field components for TE waves when Ez is 0. So for transverse electric means no component of E along Z direction. That means, that is why, so Ez is 0. So now Ez 0 you substitute in the above equations, then we get Hy, like if we substitute TE wave means transverse is 0, Ez if we put 0 in this equation, then Hy Ex is 0. Substituting these values in this, we get other components in this way, and which can have a general solution in this form, where A1 and A2 are constants.